This week we're going to finish up our look at bivariate measurement data, looking at standard 3 and 4. So let's start with looking at standard 3, where we are studying the linear model, the linear patterns in the data, and interpreting slope and intercept. So let's start by looking at our Newton's revenge information. Several of you, when you submitted your assignment from last week, used Desmos, a free online graphing calculator that is amazing and really user-friendly. So I started by clicking on this plus menu here. I was able to pop in a table and put my enter my data in here. And so here's the scatter plot that resulted. And very similar to the original problem from last week, it's very clustered together and a little bit difficult to see what's really going on. But using Desmos, we have the opportunity to zoom in and out and rescale this information really easily. So there's a nice piece using the technology. So 8th grade students learned to graph a trend line or a line of best fit. So I could estimate that going sort of through here on my graph. So this connects really nicely to some of the function standards that 8th grade students are working with. They are, through 8th grade, learning to work with linear functions, and specifically the equation y equals mx plus b, learning how slope works and learning how y-intercept works and what that means in a context. So with this problem here, one strategy for students to work on finding the slope of this line would be to use 2 points that are found on the line. They can use the equation that the difference in their y values divided by the difference in the x values can help them find the slope. Similar to the idea of rise over run, so finding the rise is subtracting the y values here. So got 145 for our y value minus 104 for our second y value, and for our x values 184 minus 153. 41 over 31. Oh, close to 4/3 that we might as well use that as the slope. Okay, as far as finding the intercept, students who redid this with the scaling that we have here, it's pretty difficult to figure out where we're going to cross by guessing where it's going to cross the y-axis to be able to see that on the graph. So we would need to actually algebraically solve that. So that might be done by using our equation y equals mx plus b, knowing that our slope, our m, is approximately 4/3, and using one of our known points. So we can use, in place of y, our 104, and in place of x, the 153, and we can simplify and solve for b. 153 simplifies to 204, and we can subtract that from both sides and find that b is approximately negative 100. And it turns out, when I take a look at what I've got here for my orange trend line, 4/3 x minus 100. An approximate equation for our line of best fit or our trend line. We can use that to extrapolate a point representing Yao Ming, the 7'6" tall basketball player. So we can, I'm going to go ahead and round his height to 229 centimeters, and we can substitute that and solve for y. Solve for his potential reach height. So 4/3, 229 less 100. 4/3 of 229 simplifies to about 305 1/3. And then less 100 gives us a reach of 205, which would mean, in this case, with this trend line, that Yao Ming would not be safe. So this problem was actually set up to be ambiguous, to depend, so students could have a nice, so various groups could have a nice argument over whether Yao Ming would be safe or not. And then you could have discussions regarding, well, if you're trying to go for safety, do you go for the worst case scenario, or do you go for the middle, the average of the data? Well, if you're trying to stock shoe sizes in a store, you could go for the average because no one's going to die or be injured because their shoe size is not available. But when it comes to a case like this, you want to go for the worst case or most outside of the box kind of situation, so you can have some discussions. Now, this calculator, this Desmos calculator, will find the best fit line for us. We'll actually do some calculations. So I just want to demonstrate real quickly how that is done. It's a really nice feature. So using my notation from this graph, I've got y1 and x1 as the variables that are already established. So I'm going to, in my next space right here, I'm going to put y1. And notice that the subscript just happens automatically. I just typed y1. And then I'm going to show my keyboard and use, go to the alphabet portion. And this little tilde gives us the idea of approximation. So I'm going to put in then mx plus b. So this is asking Desmos to calculate our line of best fit. Oops, I forgot to put the subscript for x. So pop the 1 in there, and there we go. So this is actually calculating for us the exact best potential line that goes through this data. So the slope is a little bit different, and I think with the slope of my new line, Yao Ming is probably going to be safe. We've got a slope of 1.045, so it is not as steep as the original, and an intercept of only negative 51.6. So it's a little bit off of my trend line that I estimated. So I think it's pretty neat that Desmos can do that for us, and it's a nice handy thing to know as a teacher. So typically you don't show students that Desmos will do this because we'd really like them to have the practice calculating the slope and the intercept by hand. It gives them a chance to apply their knowledge and practice finding functions on their own. Another concept that students will be working on is trying to determine the relationship between two sets of data, specifically what is the independent and the dependent variable. So here in this problem, we've got Arlie's bike ride. She is preparing for a 30-mile ride for charity, and she's been biking every weekend. In order to predict how long the charity event will take her to complete, she's been keeping track of her time and distance. So, in looking at this table, we've got distances for each time, and we need to specifically think of what is the problem, what are we trying to find, what would be the input and the output. So since we know what the number of miles is that we are training for, and we're trying to determine the outcome being the time that it will take, this means that our input will be distance, so that will be our independent variable, and our output will be the time, our dependent variable. And so that helps us determine which axis gets the distance and which axis gets the time. And one thing that's a little difficult about this is in many cases, time is always the x-axis. And in this case, it is not. So with the help of Desmos, we have our scatter plot here, with the x-axis representing our distance in miles and our y-axis representing our time in minutes. And again, we've used the handy Desmos tool that gives us the line of best fit, where we use the tilde or approximation symbol here in place of the equal sign, and that gives us the best estimated parameters, the slope being approximately 4.8 and the intercept being 25. So this is a good place for students to discuss and learn about and interpreting what does this line of best fit mean? What is the y-intercept in the context of this problem? Well, it's approximately 25, so there's 25 minutes that no riding is occurring. So at 0 miles, we've got 25 minutes. Well, a possibility is that she takes a 25-minute rest stop on each ride that she takes. That's one way to interpret what's happening here. And then what about interpreting the slope in this equation? And this can be looked at as for each additional mile that she rides, it's taking another 4.8 minutes for her to accomplish that mile ridden. Another vocabulary term that we can use here, we can extrapolate the outcome for her 30-mile ride. So if she is traveling 30 miles, we can estimate that it would take her 169 miles to accomplish that ride. That would be an extrapolation because we are making a guess according to a trend line that is outside the set of data. If we wanted to use the same trend line to figure out how long it might possibly take her to travel 10 miles, that would be considered an interpolation. It is a educated guess within the set of data, in between the data points. So that would be about 73 minutes to travel 10 miles. We could also use the equation to substitute and calculate the output, the y value for each of those cases. So there is standard 3.